Before we move to the next topic of this class, let's just see very quickly how you can use MATLAB to draw a Bode diagram. So the first thing you need to do is to declare the symbol S as the Laplace variable. This can be done with this command. Once this is done, you can declare any transfer function just by typing its value literally. So for example, the last example which we have seen was this transfer function over here. Just type it down, paying attention to write it correctly in the syntax with all the parentheses and multiplications. Once this is done, you can just use the command Bode to draw the Bode diagram. And I suggest also using this command grid on to show the grid in the background. There you go. You can also draw the Nichols diagram. Guess what? By typing the command Nichols. And there you go. Both of them. So this lets you try and verify all the transfer functions you might have. If you try to draw them by hand with the rules we've seen previously, then you can check them with this command. I also advise you to download one file that you can find on MATLAB Central. It's a Bode plot with asymptote, which is easier to compare than the smooth Bode plot. You can find it just in the MathWorks website. And this function, you will see, just throws the asymptote together with the curve. It's this one. There are several versions available. I found this one. It's called asymp. Well, it does the job. You see it over here. You have both the diagram and asymptotes at the same time. Excellent. Let's move to the next topic, which is block diagram representation. So what is a block diagram? We already seen a little bit that you can represent the system as a box with some arrows going in, the cause, let's say, the inputs, and some arrows going out, the output signals. What we would like to see here is that this representation is not limited to one box, but it is interesting to use several boxes and several interconnected boxes to represent the structure of the systems in order to make it more readable, more understandable through a visual tool. So let's say a dynamical system is in general made of several subparts, okay, and each of these subparts have simple laws, let's say, compared to the laws describing the whole system. So it is possible to make use of graphical tools in order to better visualize the presence and behavior of subsystems inside a complex system. And that's why we have we are going to introduce the block diagrams. Block diagrams basically are the combination of three kinds of elements. We have blocks, which represent transfer functions or differential equations, if you wish. We have lines with a direction, so basically arrows with an arrowhead. Do not forget the arrowhead, which represents signals. And the arrowhead is important because a signal going in is an input and the signal going out is an output. It's not the same. And then we have a sum or difference node, like this one over here. We have two signals, E1, E2, and then here we have the sum of E1 minus E2, which is the output over here. Very easy to understand graphically. So how do you create the block diagram of a system from the equation? Well, the trick is write the equations characterizing each element of the system separately. Then for each element identify the cause, the input, the arrow in, and then the output, the effect, the arrow out. There is a trick to get this easy. In most cases, if you have a variable which features a time derivative, so if your equation has time derivative of something equal to something else, the output is most likely the variable with the derivative. So we'll see some example later. So because the causality goes in that sense, okay? So the variable for which the derivative appears is most likely the effect of the other variables. So it is most likely the output. So if we assume zero initial condition and use Laplace transform, then we just write the transfer function inside each box. And then there might be algebraic relation among signals which have to be sorted out by using the nodes. So let's see some example which I hope clarifies the thing, and then also you have several examples which you can do in the tutorials with the solution. So we have a DC motor represented here. The input is the voltage outside and the output is omega m, the angular velocity of the shaft. So this system is ruled by two equations. There is an electrical equation written over here with derivative of current I appearing. So this should ring your bell. Then in this equation I would probably be the output of this system over here. Then we have a mechanical equation with the derivative of omega of the angular velocity appearing as a function of a momentum here. And then there are some electromechanical couplings given by scalar equations. So actually these are a little bit more tricky, because in these two the causality is obvious. This is the output, this is the output. Here we will see. So how do we do it? Well, we just do by little, starting with the first equation. So we take the mechanical equation, we Laplace transform it, so we get this, and then we know the output is omega m. So omega m over gamma m is 1 over Js, and we write it like this: input going to the box, transfer function inside the box, omega output outside the box. Then let's go to the second equation. There is an electromechanical coupling which says that E is Ke times omega m of t. Now omega m is already the output of something, so if we need this E somewhere, well, we can just take omega m multiplying it by Ke and we get E. And then we have gamma m, which is the input of something, so it will probably be the output of another block. Remember, it doesn't make much sense to have the same signal which is the output of two blocks, of two independent blocks. You can have the same signal going into two different blocks, but the same signal cannot be the output of two different blocks. It doesn't make sense, okay? So we use this equation over here to say that gamma is Kc times I. Pay attention, this expression over here, what is written here, depends on the arrows, okay? So remember again, this expression, this thing, means that the output is the input time what's inside the box. If you change the direction of the arrow, this will change, assuming this is possible due to causality, okay? So read this thing over here means gamma m is Kc times I. This thing over here means E, the output, is Ke times omega m, and not vice versa. Let's go now to the electrical equation. This is it. So we turn it into Laplace transformed version, and we get basically that I over the difference of two signals is this transfer function. So basically this block goes here, I is the output of this block with U minus E as input. How do we get U minus E? Well, we just put a difference node, and that's it. Everything is sorted out. So take the time to review this example and understand it as best as possible, and then please try and do the examples on the tutorials. We have another example here that I'm not going to do, but you can think it over and try to see what is the solution. I just warned that there are several different schemes possible, so everything depends on how much detail you want to put into the result. So for example, in this solution over here, you might, in this example over here, just a mass spring damper, you might want to make the velocity of the mass appear, basically the first order derivative of y. But you might not, you might just be happy having f going into a single block and having y going out. So basically the level of details and the level of complexity depend on which signal you want to make visible or not. If you are happy with only y and f appearing, well, just one block suffices. If you want to have v appearing, so derivative of y with respect to time, then you would have to make it a little bit more complex. I leave this up to you for solving. So why is it possible that we have several different solutions for the same equation? Because there are several schemes that are equivalent. So for example, imagine you have a block scheme with interconnections like this. Well, this is equivalent to this one. So basically, if you have a series interconnection, you can just replace the input-output relation with one single block containing the products of the transfer function in the two blocks. Why is it so? Well, this is very easy. Y equal this signal here times h2, and this signal here is h1 times u. So y is h2 times h1 times u. There you go, you have it here. If you have a parallel connection like this one, so y is the sum of a signal going into one box and then another box. Well, what is y? Y is h1 times u plus h2 times u. So basically h1 plus h2 times u, which is equivalent to this one. Pay attention here, there is a sum node. You cannot have the same output going out again from two different blocks. This would be a mistake. It doesn't make any sense at all. So this is a parallel connection. The last kind of equivalence that we see is the so-called feedback connection, which is actually very important, because if you remember the first class, feedback interconnection is what you see appearing in control systems. If you remember the example of the car, of the driver of the car, in the end what you have a reference signal coming in here, then you have your controller and plant, let's say, and the original system over here, and then you have a return line somewhere. So this scheme is very important because it is the general scheme of a feedback system, of a feedback control system, of a closed loop control system. So if you have this kind of scheme, you can prove very easily. You can do it yourself actually with the same trick. Just say what is y? Y is d times epsilon. What is epsilon? Is c minus m. What is m? M is r times y, and then you solve between y and c. Basically you get this expression over here. Pay attention, there is a negative feedback over here which corresponds to a plus over here. If this is not the case, then the sign will change. I just give a peek at the next slide. If you have a plus here, then you would have a minus here. So let's go back to this one, which is the classical scheme anyway. So let's have some definition over here. We call the direct transfer function d, which is the transfer function between y and epsilon. We have a feedback transfer function, we call it r, which is the one between m and r. And the most important definition in this slide is the loop transfer function. Loop transfer function is basically the product of all the boxes in the loop, so d times r, when a negative feedback is taken. And we call the closed loop transfer function the transfer function between c and y, which is this one, d divided by 1 plus rd. So I invite you to really pay attention at these definitions over here, because they are key to understand what I'm saying in the next classes. Okay, so please pay attention to this. In case we have a positive feedback over here, we still stick to the previous definition. So basically, if you have a positive feedback over here, then you can imagine we just multiply and divide by minus 1 on this line over here in order to make it appear again, and then just basically you have a minus r appearing here. So you have a minus r appearing here, you have a minus in front of the loop transfer function, and which then becomes minus rd in this case. So moral of the story, you always have to refer, when looking at this definition, to this scheme over here. If you do not have a negative feedback, just create it by multiplying twice times minus 1. So you make a minus 1 here and a minus 1 here, and then you have this scheme appearing, okay, which is equivalent to saying the loop transfer function in this case is defined as minus RD. I hope this is clear. So let's say why this is interesting, because let's see a little bit more complex scheme. You might have a more general scheme for a feedback system. If you remember again, the example of the car could be this one, and this one basically features a reference C, and P is the disturbance, if you wish. And this can be shown is equivalent to this kind of scheme over here. And you can also think it is due to the superposition properties of linear system. So what it means that when you compute the value of y due to P and C, you can compute the effect due to P by just considering C as 0, and compute the effect of C by considering P as 0. So basically the effect of P on Y will be described by F2, the effect of C on Y will be described by F1, and then this is what you are left with. And how do you compute this F1 and F2? Well, it's the same rule as you have here. So you have to identify in each case which is D and which is R. So for example, in the case of P, we have a negative feedback, so the direct line is D2, and then the feedback line is R times this one. And concerning C, from C to Y, then the identification is more straightforward. The D is just D1 times D2, and the return is R. Let's just see it here. Basically, if you assume P equal to 0, you are left with this one for C. So basically, by using the series equivalence, this one becomes this one, and then you are left with the example as we've seen before, which yields you this function. Okay, make sure you understand this one before going on. Now we see the other one, the effect of P. So we assume C equals 0, we are left with this one. We use the equivalence of the series over here. We just leave this one over here. We get this one together, the minus sign stays, and then we are left with this one. So this is basically the computation of the functions we called F1 and F2. So to wrap it up and put it together, basically Y is the sum of F1 times C plus F2 times P, and these are the functions. I just invite you to notice that the denominator of these two functions is the same, and actually this is always the case when you have a feedback loop with several inputs and several outputs. Doesn't matter which output or which input you take, the denominator of the transfer function is always the same. We can also call this transfer function with some specific names. This one, you can call it the servoing or tracking transfer function, and this one is the disturbance rejection or regulation transfer function. So just to anticipate a little bit what comes next, you understand that if your control system is tuned correctly, your Y has to be as close as possible to C regardless of P. So basically the goal of tuning a control system will be making sure that Y is as close as possible to C without any influence of P. So basically this one as close as possible to 1, the number 1, so that Y equals C, and this one as close as possible to 0, so that P, whatever it is, doesn't change Y. So that's again a reminder of what we have seen in the first class, which shows you why this scheme over here is important, because it remembers, it recalls, it is the scheme of a general control system. And in this case you understand that if this is this, if this scheme is this, you understand that D1 plays the role of the control law logic, let's say, of the reasoning that you have to apply when controlling your system, when controlling your car, your plane, whatever. So this typically is something that has to be chosen or to be designed. Okay? So again, this is the slide which clarifies what I said again. The control goals are basically having this one as close as possible to 1 and this one as close as possible to 0, as I anticipate just beforehand. Let's see a simple example of a feedback loop. So this is a simple system, first order system over here. This is the controller that we want to tune in order to achieve something. So typically C has to be followed by Y, and we assume that G is scalar. So by using the rules we've seen before, we can write Y over C, which is this one. Direct line on the numerator. Let's see again, let's see the rule again, just so we don't forget it. So the equivalent of this one is direct line on the numerator here, divide by, divide by, with feedback loop, 1 plus RD, so 1 plus the loop transfer function, the product of all the elements. So let's go back there. Numerator direct line, G times K divided by 1 plus tau S, divided by 1 plus G times K1 plus tau S. Here we have just 1, so the loop transfer function is equal to D. And then we can simplify this by simplifying the denominators that appear in this fraction, and then we are left with this one. And then, as we said before, we like to put this into canonical form, so the scalar part that doesn't depend on S is 1 plus gk. We simplify, we factorize this 1 plus gk, and we are left with this one. And this is basically Y over C. It is still a first order system, but with different K and tau. And, well, depending on the value of G that you've seen, you can have a different step response from C to Y, which is visualized here. Basically, with G growing, you get Y getting closer to C at the infinity. So this basically, you see, it's a very simple first example of tuning, which shows you that basically if you want to have your final value of Y as close as possible to C, you have an interest of getting a G as big as possible, maybe. And also, on the other hand, you can also look at tau. That tau becomes smaller, the time constant, with G growing, so you see the response is quicker if your G grows. Well, this is the first idea of how you can tune this kind of example system, and it gives the idea that basically tuning a system, you get two things you can get is reactiveness of the system, so how fast it goes from the initial value to the final value which you want to achieve, and also the precision, how close it gets. But this example is very simple, and it neglects another aspect that here is not an issue, but is an issue in the most cases, which is the issue of stability. And stability is the topic of the next class. So I hope you enjoyed this class, and it was a lot of stuff, and probably a very long class, and a bit hard. I promise you the other ones will be easier probably, but it is very important to make sure that you understood the concept over here, and especially the definitions of the closed loop, loop transfer function, and the simplifications of loop transfer function in order to get, or closed loop, sorry, in order to get the closed loop functions, to make sure that you understand what's followed up. Okay, thank you for listening, and everybody stay safe.